Hello and welcome to this lesson for OCR A-Level Physics for Module 5, the Newtonian World and Astrophysics, in the concept of gravitational fields and looking at the idea of gravitational fields themselves. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification. So we're going to be looking at 5.4.1 point and spherical masses. Now, a force field is an important concept to understand in physics, as a field is a region in the universe where an object placed inside of it can experience a non-contact force due to its position in the field. Now, the properties of the field are given by the virtual particles of the force interaction, but on the macro scale we can say that objects must contain a certain property to experience a non-contact force when placed inside the field. Now, in gravitational fields, this property is mass. So if we look at the properties of gravitational fields, we can say the following. They act on objects with mass. The fields extend to infinity, they exert weak forces, and these forces are always attractive. Now, any field in physics can be described with four main properties. The definitions of these properties is consistent among all fields. Now, learning these definitions is integral to understanding the physics of any field. So any field in physics can be described with four main properties: the law to calculate the force exerted in the field strength, the potential, and the potential difference. So the first property is the force law, and this details the force exerted between two objects when inside the field, and this is usually named after a famous scientist who's worked in this area of physics. The second property is field strength, and this details the force exerted on an object per unit property of the field due to that object being in the field, and this is down to the force the field produced. So, for example, our gravitational field strength is the force per unit mass experienced by an object inside a gravitational field. The third property is the potential, and this details the energy stored in an object per unit property of the field due to the object being in the field. Now again, this is once again due to the field being produced. So for example, gravitational potential is the gravitational potential energy stored per unit mass in an object inside a gravitational field. Now the fourth property is our potential difference. So this details the work done moving an object per unit property of the field from one point in the field to another point in the field. So the gravitational potential difference is the work done per unit mass experienced by an object moving from one point in the field to another point in the field. Now this is slightly different to the absolute potential difference, which details the work done moving an object per unit property of the field from outside the field, which we define as infinity, to a point in the field. So for example, the absolute gravitational potential difference is the work done per unit mass experienced by an object moving from outside the field to a point in the field. Now we can say that all forces between objects are either contact forces, which are forces produced when objects are physically touching. So examples of contact forces include friction, air resistance, tension and the normal force, and non-contact forces, forces produced when objects can be physically separated. Examples of non-contact forces include the gravitational force, the electrostatic force, and the magnetic force. So objects can exert non-contact forces by transmitting a field in space. So as we said before, a field is a region of space where a body can experience a force. So for example, the Earth's gravitational field is a region of space where you can experience the Earth's gravitational force, and these are represented by field lines. Now a source is always required to produce a field. For a gravitational field, this is an object with mass, and we can visualize the effect of gravitational field with field lines. Now these are drawn as straight lines from the object with arrows on them indicating their direction. Now any massive object inside a gravitational field will experience a gravitational attractive force the objects do not need to be touching. So we know gravity is a universal attractive force acting between all matter. Now different massive objects can have interacting field lines, but they cannot overlap. So field lines from massive objects can join up but not cross. So here's an example of two gravitational fields interacting. In the centre here, the resultant gravitational field is zero, as the two field lines cancel each other out as they're exerting forces in opposite directions. Now for a gravitational field, the field line should always be pointing towards the massive object. So we say the field lines should show the movement of a test mass in the field if it was placed at this point. Now, any test mass would move towards an object producing the gravitational field, as gravity is always attractive. This leads to another name for a field line, which is a line of force, as it shows the line of action of the force acting. Now, the strength of a field is determined by its field density, which is the number of field lines in a given area. In this field, the smaller the separation with the source, the denser the field lines, and the stronger the non-contact force experienced. This means in this instance, the smaller the separation between yourself and the surface of the Earth, the stronger the gravitational force experienced by the object. This indicates that as you move away from an object, the gravitational field strength decreases as the field lines spread out. The field lines spread out as a sphere, which has a surface area of 4 pi r squared. Now this happens as we assume the source is a point mass or a symmetrical object. So we know in this case the gravitational field strength decreases as a function of r squared, which is what we call a radial field. Now we note that the field extends all the way to infinity, but it gets weaker as the distance from the centre of mass of the objects increases, eventually becoming negligible at long distances. Now the field is produced from the centre of mass of the massive object producing the field. In most cases this is the geometric centre of the object. It is not the surface of the object. The lines of a gravitational field will only meet at the centre of a test mass or at the centre of mass of a massive object. Now as you can see in this diagram, the radial fields for a spherical mass and a single point mass are very similar. This means we can model even a large planet or star as a point mass with field lines converging at the centre of mass of the object. Now the density of the field lines indicates the gravitational field strength. The lower the density of the field lines, the smaller the gravitational field strength. The higher the density of the field lines, the larger the gravitational field strength. So a variation in the gravitational field strength on a surface of a planet is most likely caused by the material varying in density for the same volume. The greater the density of material for the same volume, the greater the mass, the greater the gravitational field produced. So in this instance, under the surface of K, the rocks are denser than under the surface of J. Now, the Earth's gravitational field can be mapped and minute variations can be detected. These local variations may be due to topography, e.g. mountains, craters from meteorite impacts, but also due to the composition of the Earth. Gravimetry is used in mineral prospecting as denser rocks, such as those containing metal ores, cause higher than normal local gravitational fields on the Earth's surface. And the same technique is used to search for oil. Since oil-bearing rocks have a lower density than the surrounding rock, the gravitational field strength above an oil deposit can be slightly lower than in the surrounding area. Now, objects can produce fields of two different shapes. One is called a radial field, the other is a uniform field. The radial field is produced by any particle or point mass, whilst a uniform field is assumed to be the pattern when moving close to a massive object, as it's difficult to observe the curvature. Now in both instances, the gravitational field lines point in the direction a massive object would take, but in a radial field, the gravitational field strength decreases with distance in the field, but for a uniform field, the gravitational field strength is constant throughout the field. Now in both cases, the field lines indicate the movement of a massive object placed in the field. So to summarise what we've learnt in today's lesson, gravitational fields are due to objects having mass. Modelling the mass of a spherical object as a point mass at its centre, gravitational field lines are used to map gravitational fields, and the concept of gravitational fields as being one of a number of forms of fields giving rise to a force. Now, if we've been successful and we've learnt in today's lesson, we should be able to define what a gravitational field is, model the gravitational field of a massive spherical point mass, and evaluate different gravitational force diagrams. So thank you so much for watching this lesson on gravitational fields, which is part of the gravitational fields topic in Module 5, the Newtonian World and Astrophysics of OCR A-Level Physics. Thank you so much and have a lovely day.